And the resulting is actually an increase in the vapor pressure than expected from Lawson's law to result in a positive deviation. This curve, I could only find it for ethanol and cyclohexane, but the logic will be the same. Where the cyclohexane is nonpolar, so interact with the nonpolar backbone of ethanol, which then actually blocks some of the OH group. Then the ethanol can no longer interact with the other ethanol through hydrogen bonds. 这部分有任何问题吗？ Any questions? Okay. All right. And lastly, when do you have ideal? That is the interaction in liquid A, interaction in liquid B, and the interaction in solutions are almost the same. So for a solution of very similar liquids such as benzene and toluene, then you're going to have an ideal behavior. That is the enthalpy. Let's keep showing up. I don't know why. The enthalpy of solution is very close to 0. Then the solution will obey Lawson's law. That is, you have an ideal behavior. As you can see, this is a mole fraction of 100% toluene, 100 benzene, and the measure is almost the same as ideal. Okay, so lastly, we can then summarize. Right, 所以什么时候会看到 ideal， 什么时候看到 positive， 什么时候看到 negative 呢？就是 when would you see ideal, when would you see non-ideal behavior? When the delta H of solution is 0, that means when mixing, no heat is released or absorbed. Then deviation from Lawson's law will be none. It's going to be ideal. A very good example would be benzene and toluene. Both are nonpolar, nonpolar. That means AA, BB, and AB are the same, right? And negative deviation when you have exothermic, right? When you mix these two liquids together and the solution becomes hotter. And that is when you're going to have a deviation from Lawson's law. That is negative deviation. The vapor pressure you measure is actually lower than what you expect from the Lawson's law. Why? Because of the interaction of liquid AA, liquid BB is smaller than the solution A and B, right? So acetone, dipole interaction, water, or ethanol, or chloroform are dipole again. When you mix acetone and water, you can actually form more hydrogen bonds, and will be the same when you mix acetone and chloroform together, then you have stronger interactions. So in this case, it will be dipole, hydrogen bonds, or dipole, hydrogen bonds. Right? All right. And last case, when you have a positive heat of solution, that is when you have a nonpolar, polar, and you mix them together, you only get mostly nonpolar. Then of course the interaction gets weaker, right? And the deviation from Lawson's law will be positive. The liquids want to get out of the solution because it's not stable. One example will be ethanol and hexane, where the hydrophobic of hexane will actually block the OH group of ethanol, such that OH group of ethanol cannot interact with the other OH group. And that means the interaction of AA, in this case ethanol will be hydrogen bond. BB, in this case hexane will be nonpolar interaction, is stronger than the corresponding solution, AB, which will be nonpolar, right? Because it cannot form hydrogen bond. Okay, any questions? Okay, and then remember this table is very important. You don't need to remember the numbers, but you need to know how to judge the strengths. Right? Ion dipole is going to be the strongest, hydrogen bond will be the second, dipole is the third, ion induced dipole will be the fourth, dipole induced dipole will be the fifth, and dispersion, nonpolar, or London, a lot of names for this, van der Waals is the weakest. Okay. 好 Any questions? 好 Let's continue. Alright, so we are halfway through. We are getting to the kind of all the mathematical part, right? So we just learned about Henry's law. That describes how a partial pressure of a particular gas, when that increases, how that will change the solubility of that gas in the solution, related by Henry's law. You can use concentration or mole fraction. The other one will be, what if you mix two liquids together, each of them have a corresponding partial pressure, their own partial pressure, then the total partial pressure is the sum of the corresponding partial pressure, which can be calculated by Lawson's law. That is, the partial pressure of A is the mole fraction of A times its pure form pressure, right? PA equals to PA naught in its pure form multiplied by mole fraction. Of course, then we have non-ideal behaviors. The second part is, what if we add salts into liquids? We still make solutions. How that actually affects the property of that liquid. First thing is called boiling point elevation. that is the boiling point of that solution will increase compared to the pure form. A non-volatile solid like table salts elevates the boiling point of the solution of the solvent by the equation showing this. Delta T, the increased temperature, is Kb, a constant multiplied by molality. Watch out, we are using molality here, not molarity. That is the mole number divided by kilograms of the solvent. Where delta T is a boiling point elevation, or the difference between the boiling point of the solution and that of the pure solvent. So water 100 degrees and maybe 105. Kb is the constant, that is the characteristic of the solvent, right? So Kb only depends on the solvent. It's water, it's going to have a corresponding Kb. If it's ethanol, it's going to have another Kb. It has nothing to do with you add sodium chloride, you add potassium chloride, it doesn't matter. It's actually a property of the solvent. And it's called the molio, right? It's a molarity, molio boiling point elevation constant. And M, solute, is the molality, mole per kilogram of the solute in the solution. And of course, for water, at 25 degrees, kilograms equals to liter, right? They are the same. Okay, the other one is the freezing point depression. That means boiling point increases, but freezing point decreases. When the solute is dissolved in a solvent, the freezing point of the solution is lower than that of the pure solvent. And of course, delta T will be negative. Is Kf, freezing point depression constant multiplied by molality of the solute. Where delta T is a freezing point depression, so it's negative, or the difference between the freezing point of the pure solvent and that of the solution. Well, we'll change the sign here. Kf is constant is characteristic of the particular solvent. Again, Kf and Kb are both characteristic of the solvent. Has nothing to do with what solute you add. Not exactly. We'll see. It's called the molar freezing point depression constant. Okay. So the consequences is like this, right? So you can imagine that this will be the pressure of water or any solvent. And what happens is when you add solute, the pressure freezing point of water. Okay, so this is the freezing point of water at this point. This is the boiling point of water. But when you add like sodium chloride, the boiling point will increase. When you add sodium chloride, the freezing point will decrease, such that original curve is like this, and right now final curve is like this, right? Because we need to actually connect it. Okay. And here are just some examples of the Kb's and Kf, which we'll see some examples later, right? So water has a small Kb and has a small Kf. Carbon tetrachloride has a kind of a moderate Kb and has a large Kf. Okay. All right. So we are actually going to watch a video to understand why. What's the reason for this? Right. So molecularly, how do we think about this? Originally, you imagine that either both the points, melting point and boiling point, to increase or to decrease. But what really happens is the range gets higher. Right. Boiling point increase, melting point decrease. And what really happens is shown here. Okay.
City, trucks adding salt onto icy roads might be very familiar to you. But do you know why salt is added to icy roads? You will find that out in next few minutes. Rock salt is mostly used to melt ice since it's less expensive and readily available. Rock salt, which is formed by the evaporation of ancient seas, is mined from underground as a dry crystal salt. Do you know how much salt is used in the United States per year? More than 20 million tons of rock salt is added onto the roads each year in the United States. A water molecule has 2 hydrogen atoms and 1 oxygen atom. Hydrogen bonds can be formed between these water molecules. In the liquid form, water molecules move freely. When water freezes to make ice, these water molecules form an ordered structure. At the freezing point, there's an equilibrium between liquid water and ice. Therefore, a thin layer of water can be found on the surface of ice. At equilibrium, some water molecules freeze and the same amount of frozen water molecules melt. Therefore, the amount of ice and water will not change. When we add salt into this water-ice mixture, that equilibrium is disturbed. Now, let's see how salt melts ice. When salt is dissolved in water, it generates sodium and chloride ions. These ions disrupt the formation of the ordered structure of water molecules, or ice. As a result of this, the amount of water molecules that freeze will be lower than the amount of water molecules that melt. So, the ice would start to melt. Now, the salty water freezes at a temperature lower than 0 degrees Celsius or 32 degrees Fahrenheit. This process is known as the freezing point depression. In other words, salty water has a lower freezing point compared to pure water. Higher the salt concentration, lower the freezing point. But there's a limit. Rock salt is not effective below minus 9 degrees Celsius or 16 degrees Fahrenheit. Below this temperature, calcium chloride and magnesium chloride can be used as alternatives to rock salt, but they are not cheap or readily available as rock salt. The downside of salt is its negative impact on the environment. Salt is a very corrosive material and it directly affects the vegetation. That's why in some areas you can see reduced salt area signs in highways. A small amount of salt is used in these areas to protect the vegetation. Remember, 20 million tons of salt is added onto the roads in the United States per year. There are alternative chemicals that can be used instead of rock salts such as urea and calcium magnesium acetate, which are less harmful to the environment compared to rock salt, but they are more expensive. Even though salt is not environmentally friendly, it saves thousands of lives every year. So, you still have an opportunity to innovate an inexpensive and environmentally friendly method for ice melting. Think about it. Be found on ice and see how salt melts and melt.
Okay.
So, ice.
Okay. So what really happens for freezing point depression is to freeze, we need water molecules in liquid state where they move around. They still have hydrogen bond, but they are moving around freely. They need to pack into these periodic lattice, these hexagonal lattice. What really happens is when you have sodium chloride dissolved, form stronger ion dipole bonds than hydrogen bonds, it breaks the lattice. Right now, water molecule cannot form periodic lattice. So what happens is right now they're just moving freely around. They behave more like liquids, hence, of course, they have more vapor pressure. So in order to actually force them into a periodic lattice, you then reduce the temperature such that they start moving more slowly, then they stay steady. It's the simple boiling point elevation. How does it boil? You need to break the interaction, right? So it actually goes into gas phase. What happens is, right now, we have even stronger interaction, sodium ion dipole interaction, which is stronger than hydrogen bond. So it's very hard for the water molecule to get away because you have a really strong positive charge and negative charge that holds them together. Since it's very hard for the water to go into gas phase as a liquid, on the other hand, it's also very hard for water to form a periodic lattice because the structure is broken by the stronger interaction. Hence, we have a boiling point elevation, we have freezing point depression. Okay, any questions?
As a result of this, the amount of water
因为 boiling point 的 boiling 是什么意思呢 ？boiling 就是在 liquid state 里面，他们还是有 hydrogen bond， 虽然他们没有这个 periodic lattice， 但他们还是在中间还是有 interaction。那变成 gas 是什么？变成 gas 就是我要把这 interaction 的可能拉掉，拉到空气中，同意哈？那现在我本来只需要 break hydrogen bond， 对，因为它就遇到 hydrogen bond， 但现在我有 sodium chloride 在里面，它 ion dipole 它更强键结，所以你要用更多的能量才可以把它提出来。那 freezing point depression 是因为它的 lattice 被破坏。好 ，so let me repeat it in English again. So he just asked, so can I actually explain the boiling point elevation again? So you can imagine for water molecule as a liquid state, what really happens is they are still hydrogen bonded, but they don't need to form periodic lattice, right? So they are still kind of bonding to each other, but they are freely moving. For it to actually get into gas phase, you really need to break two hydrogen bonds, right? To get this molecule into gas phase, water molecule. Right. So originally you just need to heat up the temperature enough to break hydrogen bonds. But right now you have a sodium, which forms ion dipole interaction, which is stronger than hydrogen bond. So of course you need to actually have higher temperature to break this ion dipole interaction, so this water molecule go into gas phase. On the other hand, for freezing point depression, it breaks the periodic lattice. Right? So you need to decrease the energy more in order to form a periodic lattice. 好，还有其他问题吗？好 ，OK。Okay. All right. So again, it goes back to this table. So you can imagine this table is very, very important. Please remember this table. You don't need to remember the numbers, but remember the rankings and the corresponding examples. Okay. All right. And of course, we have more things, unfortunately, for solutions, and there are a lot of equations. Reminding you again, we just learned about Henry's law. We just learned about Lorentz law. 3 conditions of lossless flow: ideal, positive, negative. And then right now we learn about freezing point depression, Kf, and boiling point elevation, Kb. And now we have more equations. Osmotic pressure. A solution and pure solvent are separated by a semi-permeable membrane. This is very important. You need to separate them so the ions are not moving around. Otherwise, diffusion will just homogenize the whole solution, right? Which allows solvent but not the solvent molecule to pass. How? For example, sodium chloride has charge, right? So what if your membrane actually repels charge? You have a very hydrophobic membrane. Of course, charge won't come through. But what if your solvent is less polar? Then of course, solvent can pass through. As time passes, the volume of the solution increases, whereas that of the solvent decreases. This flow of solvent into the solution through the semi-permeable membrane is called osmosis. 渗透压. Osmosis is a very important thing. Why? Because actually how our blood works is actually through osmosis and reverse osmosis. 那基本上我们的血液你的血管就是在做这件事情，渗透压跟反渗透压。你心脏在打的那一瞬间，实际上就是怎么样，让你动脉的压力非常的大。你动脉压力非常大会怎么样？导致收入就会溶到你的细胞液里面。反过来，你的静脉压力小，所以就会反向流过来。Eventually liquid， 然后你的肾脏的目的就是为了保证这个平衡。所以为什么有些人洗肾，就是因为他的身体里面的这个 osmotic pressure 有问题，那他肾脏的function不太好。Eventually, the liquid levels stop changing, indicating that the system has reached equilibrium. Because the liquid levels are different at this point, there is a greater hydrostatic pressure on the solution than the pure solid. And this extra pressure is called osmotic pressure. Of course, this might sound kind of a bit abstract. Let's look at an example. Right. So imagine this green is a solution, say a water solvent with some salt inside. These green salts. And then you put this whole thing into a beaker with a semi-permeable membrane that only allow this blue sphere to pass through, right? Only allow the sodium molecule to pass through. But in the outside the beaker, inside the beaker, you have pure water. What happens is the osmotic pressure of inside is higher than osmotic pressure of outside is higher than inside, right? Because inside you have more salt, so vapor pressure will decrease, right? So the pressure is lower, pressure is higher, so pressure goes from low to high, so you're going to have more water molecule going through the membrane into the flask. Until when? Until you have a final like this. Of course, you can never get the pressure to be the same, but then you're going to create, you can see the height increase, right? Height goes from here to all the way here. Then the difference is called osmotic pressure. Osmotic pressure, 渗透压, right? And of course, you can have you can do this by active osmosis. That way, you can increase the pressure, right? I just said that the pressure in the pure solvent is higher. The pressure in the solution is lower. Why? Because the greens are non-volatile ions, right? Non-volatile solids. So the pressure due to the non-volatile solids gets lower. So of course, osmotic pressure will apply where the solvent will automatically go through the membrane into this part to increase the pressure here, dilute the solid, right? And then such that finally the pressure difference equals osmotic pressure. So of course, what you can do is you can apply a pressure on this side, such that the pressure of the solution becomes higher, such that no osmotic motion has occurred. Right? So that's something you can do. And 这就是我们的心脏做的事情，就是大量压力导致你的血管里面的那个渗透压上升。Okay, this is exactly what our heart does, right? So it actually pumps with a high pressure into the arteries. All right, and then if without pressure, then you can see the difference will be that osmotic pressure, just like previously. Okay, now we have an equation. Unfortunately, more equations. Right? So property of solutions has a lot of equations you need to memorize. All of them you need to memorize, and all of them will show up on the exam. Okay, so to describe the observed correlation between the change in height and the corresponding concentration of the solute inside that solution, we can use something called Van Hoff's equation. So as you can see, Van Hoff again, right? So Van Hoff really focused his entire career on studying solutions, right? Such that the osmotic pressure, the difference in height, is directly equal to nRT, not 节律，这不是节律，nRT. N is molarity. Now we are using molarity. So only for freezing point depression and boiling point elevation we use molarity. Here we use molarity. R is the ideal gas constant and T is temperature in Kelvin and pi is osmotic pressure. If you look closer at this equation, do you see something that you've seen before? Yes, indeed. This is ideal gas law. P equals to mRT. M is concentration, which is N divided by V, right? Number of particles divided by volumes, or moles of particle divided by volume. If you multiply by both sides by V, you get PV equals to nRT. That is indeed ideal gas law. So indeed, the osmotic pressure equation by Van Hoff's equation for osmotic pressure is indeed ideal gas law, but for solutions. So you can imagine these solids are like ideal gases inside this solvent, and it causes the pressure of the solution to decrease. And of course, we know ideal gas law doesn't really apply for real gas. So of course, we're going to see non-ideal behavior for osmotic pressure as well. One can find that it resembles the ideal gas law indeed for a dilute solution. So keyword need to be very, very dilute, such that the solute and solute not interacting. The equation for its osmotic pressure is related to ideal gas law. PV equals to nRT divided both sides by V. Then you can have N divided by V, which is molarity. Then PV equals to molarity divided by RT. That is for osmotic pressure. And of course, if we apply pressure on the other side high enough, we can do the opposite. That is, we can push solvent from a solution into a pure solvent. And why is this important? You can imagine if you want clean water, you can actually use this. 所以在沙漠中尤其像中东那些比较缺水，还有像新加坡比较缺水的地方，有些人的想法就是直接收集尿液啦。不知道大家有没有看那个沙丘对不对？沙丘一跟沙丘第 anyone see Dome, right? The movie Dome, right? So they have this suit that collects the water, right? And indeed, you can imagine the suit is doing reverse osmosis. 好，反正都要。And like I mentioned, this is although in Taiwan water is kind of a very not a scarce resources, but water is actually a very scarce resources in many places in the world, Middle East, Singapore. So actually a lot of research goes into how do we actually perform reverse osmosis. You can imagine you apply pressure, that means what? You need to apply energy in order to pressurize this. How do you minimize the amount of energy you need to actually maximize the separation of solvent and solute? And this is one of the desalination plants.
Desalination is an important pillar of Singapore's water supply system. Like new water, it is a weather-independent source and strengthens the drought resilience of our water system. Desalinated water is expected to meet up to 30% of Singapore's future water demand by 2060. Built in the west of Singapore, Tuas Desalination Plant brings Singapore a step closer towards its water supply goals.
Tuas Desalination Plant will help us further expand Singapore's water supply system to meet the growing demand in a reliable manner. The plant can produce 136,000 cubic meters or 30 million gallons of drinking water daily. That is equivalent to 54 Olympic-sized swimming pools of drinking water each day.
The plant draws seawater from the western straits of Johor. Underwater pipelines 2.2 meters in diameter had to be constructed to extract the seawater. Using cranes mounted on sea barges, segments of the pipeline were firstly lowered into position before they are joined in place by divers. The pipelines are connected to 5 high-capacity pumps. Each of the pumps is capable of extracting 3,250 cubic meters of seawater per hour. Several screens were also installed to remove debris and large suspended particles from the seawater before it is sent for pretreatment.
2 more minutes.
Through the use of dissolved air filtration and ultrafiltration, the pretreatment process conditions the seawater before it's treated by the reverse osmosis system. This helps to prevent membrane fouling and preserve the lifespan of reverse osmosis membranes.
The low-pressure ultrafiltration membranes are able to remove suspended solids of up to 0.01 microns. This is 10,000 times smaller than the size of human hair. After pretreatment, the water undergoes reverse osmosis, the heart of the desalination process.
Tuas Desalination Plant is equipped with over 14,000 reverse osmosis membranes. The semi-permeable membranes remove salt content of up to 35,000 parts per million. This is equivalent to 30 grams of salt per liter of water. At Tuas Desalination Plant, the pre-treated seawater undergoes a two-pass process to ensure a higher quality permeate.
During the reverse osmosis process, the feed water is pumped into the membranes at high pressure. The larger salt particles are trapped by the membranes, and only freshwater particles are allowed to pass through. The product water from the reverse osmosis process is disinfected with sodium hydrochloride and remineralized with carbon dioxide are allowed to pass through. Salt particles are trapped by the membranes, and only freshwater particles.
So you can imagine that the membrane doesn't need to be a single layer, not between two sides, right? What they made was the membrane can be a spherical membrane, so you can actually just curl around the membrane such that you rotate multiple times. And every time you apply the pressure on the water, such that the solution, the solvent in the solution will just go into the second layer due to the pressure, and then the kind of purified solution will go through another layer, go through another layer, go through another layer, go through another layer until it hits the middle and water goes through. So it's kind of a smart design. Okay, so just to tell you that the thing we learned today actually have a lot of real life implication. No matter in winter when the road freezes over, or no matter for places in the world where we have actually water is a scarce resource. Okay.
Particles.
All right. So like I mentioned, it's an ideal gas law, right? PV equals nRT divided by FIV, and of course a lot of times things are not ideal, right? So reality is we almost never have super ideal solutions, right? And what really happens is for non-ideal solutions, you have this concept called I, that corrects for this non-ideal behavior. The proportionality between osmotic pressure and the concentration of electrolyte solutions, right? When you dissolve like sodium chloride, magnesium chloride, can be derived. This is corrected by Van Hoff's index I. I equals to I MRT, and this index describes the actual amount of particles in solution over the amount dissolved. Now this I equals to moles of particles in solution divided by moles of solid dissolved, right? So you dissolve sodium chloride, say 1 mole. You expect to get 1 mole of sodium plus, 1 mole of chloride plus, minus, right? So that means I will be 2 number of moles of particle in solution. Is particle solid dissolved. Moles of solid dissolved will be 1 because you have 1 mole of sodium chloride. Moles of particle in solution will be 2, right? Because 1 particle of sodium, 1 particle of chloride, okay, minus. But in reality, some of the sodium chloride may not purely dissolve in solution, so you might only have 1.7, 1.8, right? So indeed, what really happens is you're going to have something called ion pairs, right? Some of them actually still behave like it's a single particle instead of 2 particles, right? You don't have a complete dissolution. So you can imagine a cation and anion, some of them still form ion pairs. So you actually don't have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 particles. You only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles, right? So you can imagine this is going to be what? 80% reduction in the osmotic pressure, all right? And then lastly, we can then come up with a table. Of course, you can imagine if the stronger the interactions among the ions, the less they are going to dissolve completely. So sodium chloride is kind of a well-behaving electrolyte, so you expect it to be 2 because each mole will dissolve into sodium plus, chloride minus. But what really observed experimentally is 1.9. That means you still have 5% of sodium chloride behaves like a single particle. Magnesium chloride, 1 magnesium and 2 chlorides, 3.0, but we only see 2.7. That is 90%. And you can imagine why, because magnesium is 2 plus, chloride is 1 minus. Sodium is plus, chloride is minus, right? So magnesium chloride will going to have stronger interaction due to Coulombic interaction. So of course, more charge, more non-ideal behavior. Magnesium sulfate, you can imagine really worse behavior, right? 2 plus, 2 minus. 2.0, you only have 1.3, right? You have 35% reduction. Iron chloride and so on. And you can see those are not electrolytes, meaning that they don't dissociate at all. 1 mole for 1 mole. glucose, for example, you get 1.0, 1.0, right? It's more ideal. Right? So any questions this part? And I think, okay. So I think I'm going to close earlier, which is fantastic, but I'm actually going to go back. So one thing that I didn't tell you, and this is common on exam 2. This is also common if you are actually a chemistry major or whatever major and you want to be going to a chemistry graduate school. These kind of questions will definitely show up on your entry exam. And one of the trick that the professor who actually, generate the exam usually do is, if you go back to freezing point, remember everything this is about solution, so they all apply to each other. And if you look at this equation here, for example, boiling point elevation, delta T equals to Kb multiplied by molality solute, right? So the boiling point will increase from 100 degrees, say 100.5 degrees Celsius, and Kb is just a constant you read out of table. What's M? M is the molality of solute. But what if the solute is sodium chloride? Think about this. So for example, we have sodium chloride. And we just give it to water, right? Dissolve it in water. What we're going to get, if you are lazy, you're going to write it like this, right? It's vigorous. But in reality, it's not. Right? It's so let's say we have 1 liter, 1 kilograms of water. Okay? And let's say we start with 1 mole of sodium chloride. What's the result of molality? Well, the molality in this case will be NaCl, right? Naively, you will just take 1 mole divided by 1 kilo. Mole, right? But this is wrong. So if you use this to plug in the equation, delta T equals to Kb, capital K, and NaCl, then you'll get it wrong. Why? Because when you dissolve, you actually create 2 particles. So M here is the number of particles, not the number of solutes you put in. Right? So the real case is equals to 1 mole, 1 kilo, plus 1 mole. Is 2 mole. Okay, so watch out for this. This is a trick. And it's exactly the same. In osmotic pressure, it's going to be 2. And of course, we have I, which is 1.9, but let's forget about that now. And of course, for this, it's going to be 2 mole, right? So watch out for this. This is a trick that people usually play. And of course, if I make your life harder, then I can say, actually, sodium chloride is known to have the Hobbs index I of 1.9. NaCl. And of course, this number should be instead 1.9. So it's indeed the same. Everything applies to osmotic pressure, applies to melting point, boiling point, applies to anything. Now you have a non-volatile solute, electrolyte. Or if it's a molecule like glucose, that doesn't really matter, it's just 1 to 1. Then it's 1 years. So for example, if you have magnesium chloride, right, which will be 1 magnesium 2 plus, 2 chloride minus, then you are going to have multiplied by 3. Right? And if I tell you I of magnesium chloride, like previously shown, is 2.7, then instead of 3, it should be 2.7. Right? Alright, any questions here? 这部分有任何问题吗？这是一个很常见的 trick 哦，就是我们很常想，就是那个东西被 dissolve 的嘛，那它销量多少？但是别忘了，是 particle 在 solution 做事情，而不是它在 solution 做事情，所以里面有多少 particle 才是那个 what's matter 哦。好 ，Alright, I'm finishing up early today. That's fantastic. And just a quick reminder: a lot of equation today. So liquids and solids are hard. Popular solution are equation intensive. Quickly going through this. So what we learned today, oh, sorry, I forgot to mention, we had the first equation we learned was delta H solution equals delta H1 plus delta H2 plus delta H3. And that is the breaking of the solute, breaking of the solvent, and then the formation of the solute-solvent interaction. This number may not be negative because we also have entropic correction. And the last two terms, delta H2, delta H3, because we cannot really measure how water molecule break apart, right? We can actually measure how salts becomes lattice, right? Lattice energy, like this. This is something we can measure. Then we call delta H2, delta H3 together is energy of hydration. You just do measure the whole energy, and you measure the latest energy, and the difference is energy of hydration, right? Okay. And the second part we learned is, and of course there are some polarity effects, structural effects, right? Smaller, easier to dissolve, polar, dissolve polar, okay? And pressure effects, mostly on gas, right? So because then finally we have the Henry's law constant. Partial pressure of gas A equals to Henry's law constant multiplied by the concentration of gas A in solution. So you can directly relate the head-space pressure to the concentration. You could also be more fraction, they are the same, just by some conversion constants. Right? And for temperature effects, salts increases, some exceptions, gas decreases, right? Because these are entropy driven. And when we learn about spontaneity, we'll learn more about entropy. All right. For vapor pressure, you've learned this before. You have the Van Hoff's equation that relates the partial pressure of that gas to the corresponding temperature. At a particular temperature, that pressure was measured. And the slope is minus delta H naught divided by R. The y-intercept is delta S naught divided by R. Okay? And then you can imagine that now having a salt dissolving solution, how does that affect the vapor pressure of that solution or that solvent? Well, it's directly related to the mole fraction of that solvent, right? And to the corresponding pure solvent vapor pressure. And this is Laus's law. All right. And of course, we can combine if we mix liquid, not liquid and solid, right? Then the total pressure is just the sum of the corresponding vapor pressures, which is mole fraction times pure pressure, mole fraction times pure pressure. Then we can get a curve like this. This is ideal behavior. We can also have non-ideal behavior, positive deviation, negative deviation from Laus's law. And of course, some examples you need to remember, and how does that actually related to heat of solution, which we just learned the very first equation, right? Delta H1 plus delta H2 plus delta H3. You know this? Okay. Later on, we learn about how actually salt affects the boiling point and melting point of the solution. Boiling point elevation, Kb multiplied by molality, Kf multiplied by molality. I'm kind of fast because I've gone through this, right? Okay. And osmotic pressure, right? Again, salt dissolved in solvent. And how would that affect another same solvent if it's connected to separated by a semi-permeable membrane? The result is the pure solvent has higher vapor pressure. The pure solvent has higher vapor pressure and the solution at low pressure due to what? Due to Laus's law, right? And of course, you can apply pressure to equate the pressure, or osmotic pressure will build up, right? You're going to get a pressure difference. And then this is related by ideal gas law, PV equals to nRT divided both by V. You get pi osmotic pressure equals to mRT, where M is the concentration, right? And of course, there are non-ideal behavior where you multiply I, where not all solutes dissolve freely in solutions, right? And you're going to have different I's for different solutions. Any questions? 好，这全部都要记哦，全部功都要记。You need to memorize all the equations here, unfortunately. All right, and as you can see, we saw Van Hoff's again and again and again, right? So of course, Van Hoff's won the Nobel Prize. For his work on the laws of chemical dynamics, right? How does the solute affects the interaction of the solvents and etc. The corresponding macroscopic behavior, osmotic pressure, boiling point, melting point, and vapor pressure, etc. Jacobus Henricus Van Hoff, 是 Dutch, I think he's Dutch. Won the Nobel Prize in Chemistry in 1901 for his studies in the properties of solutions. All right, and the key today, I'm going to make a quick announcement for everyone who came in late. So remember, next Monday, we're going to have exam 2. It's going to be things which will be covered will be covalent bondings, liquids and solids, property of solutions. I think I'm missing one thing. Okay, again. Alright, so next Monday, we're going to have the exam 2. So make sure if you, sometimes you actually sleep in and come in late, make sure to actually arrive on time. It's again, just like exam 1, 10:10 to 11:50. It's going to cover covalent bonding, liquid solids, and solutions. And on Wednesday, instead of going through exam 2, we're going to have another topic. Since AI won the Nobel Prize this year, we're going to talk about AI for chemistry, which will happen on final exam, right? So make sure to come to the class on Wednesday. And don't worry, the slides will still be online. So if you don't come, that's fine. You can just read the slides online. So there will be some questions regarding it. It's kind of the new things in all the fields nowadays, right? Okay. And exam 2 will just be like exam 1. 25 questions, answer cards, multiple choices. Right? Any questions? 有任何问题吗? And we're going to give you the answer key today, and then we're going to call the class today. Alright? And the answer key is the most important date. Exam 2 is on November 18th. Right? So make sure to arrive on time.